this new chapter, which is called model fitting. As this cartoon is showing, model fitting is by necessity an oversimplification of reality. So the job of model fitting is to fit a mathematical model to data that we have in order to do something about the data. For example, in order to predict when some resources in a computer system will come to exhaustion. Many servers, for example, have memory leaks. So if we count the usage of the memory, it typically, for many applications, it increases over time. A solution is to fix the memory leaks, but sometimes this is not possible. If it's not possible, another solution is to fit a model to what we see in order to be able to predict when the memory will become a problem and take actions before it happens. So in order to do such a thing, we need to go through model fitting. And what we will see is what are the pitfalls and traps that can easily come when we use standard packages for model fitting. So let's illustrate the point with this virus infection data. This is not COVID infection, this is computer virus infection. At the beginning of an infection, the growth of the infection is exponential. Most models predict this, and this is what we see for all infections. Of course, this will not grow exponentially forever. After some point, the growth will become logistic when everyone is infected, but for many systems, hopefully, we don't get there. Assume you want to control this growth, and you want to capture, for example, the rate of growth. So how can you do that? Well, the first thing is you propose an explanatory model. Explanatory in the sense of data analysis, not in the sense of the biology or the computer hacking problem here, of this kind. The number of infected hosts at time t grows exponentially. If I start with 0, at time t0 is the beginning of the infection, an exponential function of this form appears to be appropriate. Then we're interested in the growth rate, which is alpha, which will help us do some actions, right? So how do we estimate alpha? Well, we can use a package that will do standard fitting. So we have a point, a set of points, those are the blue points. We measure every hour. For example, here we measure the number, the size of the population. That gives us the blue points. And we want to fit an exponential curve. So we can use, for example, least square fit, which is the very commonly used method, perhaps the most commonly used method, that will find an exponential curve that minimizes the quadratic error. So the Euclidean distance between the blue points and the points that should be if they would be on the red curves here. So we can do this. And if we do this, we can estimate alpha, which is the parameter of this growth here. By knowing alpha, we know the mean doubling time, and the doubling time here we find 1.34 hours. And perhaps what we're interested is what will happen in +6 hours. And here the prediction is that in +6 hours, the total infected population will be 100,000 hosts. So that's a first result of our modeling. Now, if you follow the previous lectures, you should ask yourself, yeah, but what is the natural scale that I should use for doing my fitting? And if you want to fit an exponential growth, I think many of us would say, well, it's more natural to fit the logarithm of the data, because then in logarithmic scale on the y-axis, an exponential growth would correspond to a straight line here. So if I put log scale on the y-axis only, I will have a straight line here. And fitting a straight line is perhaps visually and practically easier, so that's a natural thing to do. So I can do the same thing in log scale. Again, I have the blue points, which are my data, and then I fit a straight line here, for example, by asking NumPy or MATLAB to do least square fit here. If I do this, I find slightly different numbers. I find an alpha that is different, a mean doubling time that is different, and a prediction at +6 hours also that is significantly different. Right? Instead of 100,000, we find 39,000. So in reality, what we have obtained is two different fits. Here is the red one, here is the green one. So both are not exactly the same. They are roughly the same, but as we can see, towards the future, they tend to go very differently, which is why the two predictions, the red in natural scale, the green in log scale, would have very large variance for the future. So that leaves the question is, which scale should we use here? So may I try to find your opinion about this? What would you do if you have to continue this exercise? I close the poll in a second. Closing now. And the majority is in favor of the log scale, which is perhaps right, but the argument is because it's better adapted to exponential growth, which is also perhaps right. But there is also some value to the other arguments. And why would you want to change the scale? If nature comes with a given scale, you need an argument for that. So the true reason is that at this stage, none of these two arguments is really helping us to discriminate between the two methods. In order to know what scale we should use, or more generally, is a model fitting exercise correctly posed, is this model good? We need to go more into what statisticians think about this. So we have here a model of the type, we have some data, y, well, that we want to fit to some function with an unknown parameter theta. And the fit is never perfect. If the fit would be perfect, one, that would be suspicious, and second, there would be no problem. So there is an error term, which we call noise here. So the problem is to estimate the unknown parameter theta. For example, here, if you voted for the natural scale, this is your model. If you voted for the log scale, this is your model here. So of course, there is a one-to-one mapping between log A and alpha. So those two models essentially are the same here. They're equivalent with a parameter that has two components, A, the initial value here, and alpha, which is the rate of growth of the system. So if we put it like this, the two models are essentially equivalent, so there's no difference here. However, when we do the fitting, we use, for example, least square. That means we use the package that minimizes a score. So I call it the signal processing interpretation, as opposed to the statistical interpretation. In signal processing, we do things, we look whether they work, and if they work, we find we're happy, and then we try to find algorithms that make it as good as possible. So in the signal processing interpretation, we have to choose the score. The score that I mentioned implicitly in the two cases was the least square. The least square means this penalty is considered for the error term. So if there is no noise, we have equality between y and f, but there is a difference. So for a given value of theta, I compute the error, which is y minus f. I call it noise, and the L2 norm of the noise is the score that's corresponding to the least square. So least square fitting means find the value of theta that minimizes this score. We can also use very often weighted least square, and then the question is, what should the weights be? We can also use, instead of quadratic error term, we can use L1 error term. Instead of squaring, we don't square, we take the absolute value and we can weight them. Here are at least 4 very frequently used weights, the most frequently used weight being by far the first here. So what should we do and why? So in signal processing, then you try to have base cases by comparing what is the effect of using one versus the other. So for example, what we could do for our exercise here of predicting what will happen 6 hours ahead of time, we could use data from the past, try one score and see how well it predicts the future, and see which of the methods can be used. That, of course, works always well, but there is perhaps a smarter interpretation if we have enough leverage on our model, which is to use a statistical interpretation. So the interpretation that statisticians do is that the data that we see is the output of a stochastic system, which in our terminology, in a computer science view, is a simulator. So the simulator is some code, like you do in the labs, that has some parameters theta, and what we see, the data we have, is only the output of the simulator. We don't know the theta, and we want to estimate it. But in order to estimate it, if we want to use statistical methods, we are forced to model the entire simulator, including the error terms. So the simulator will output not exactly f, the result of fi of theta, but you will do that plus some noise. If there would be no noise, of course, the fitting would be very easy. For example, in log scale, if all the points are strictly on the line, 2 points would be enough to do the fitting. But as we know, this is never the case here. So the key things that we need to do if we want to use statistical methods, the key thing to remember is that we need to model the noise term. For example, we could say the value that we see is the theoretical value plus some error term, and the error terms all have the same distribution, which is a noise. So a noise is typically a distribution that has zero mean, and very often we assume the noise is Gaussian by tradition, perhaps. We'll talk about that a bit later. That's a very frequently used model. Another model is this one. It says, well, the deviation from the value is in relative terms. So that means the true value that is here is not what we will observe. What we will observe is the true value multiplied by 1 plus noise, which means if we divide by the true value, the relative error is epsilon I, which is has a constant distribution here. That's a second model. There's a difference between the two models here. The first model is assuming that the error is of the same magnitude, is random, of course, but of the same magnitude at all data points. Here we assume that the error, the relative magnitude of the error is the same, or in other words, the error is proportional to the unknown value. So the larger the value, the larger the error. Which case are we in? It depends. But most of the time, we are more in case 2 than in case 1. We can be also in intermediate cases where the error grows like the unknown data, but not linearly. So that depends on the assumptions you're able to make with your model. Another model, which is in log scale here, consists in saying in log scales, the error is like for the first model of the same magnitude at all points. There are 3 models, and of course you could combine the elements I've given and have much more, many models. For each of these models, now, because we model the noise, we also have another parameter, which is the variance of the noise here. Those 3 models are not equivalent. If you do a simulator that produces an IID sequence from these 3 models, so the only thing that is IID that you need to simulate is the epsilons. So you ask MATLAB to generate n values of epsilon, and then you compute 1, 2, or 3, you will obtain things that are random, but that are not equivalent. They are not equivalent because the distributions of y is not the same in the 3 cases here. Here, y is Gaussian with a fixed variance, plus here the term changes only the mean. So epsilon is a random variable that is 0 mean, but with some variance sigma square. We add something which for every I, when I is given, ti is known. So this is a constant. This is non-random. So the variance of yi is sigma squared. Same variance at all data points. So the unknown part, the noise part, has the same variance everywhere. Here, the variance, if y is equal to the theoretical value, plus epsilon times the theoretical value. So the variance increases like the square of the theoretical value. The standard deviation increases like the theoretical value. So we see those 2 models are not equivalent. And here we can see with a bit more of reasoning that we'll discuss later, that here the distribution is not Gaussian at all for y. So none of these are equivalent. So the first thing to remember, when we start using a statistical method, we need to reason also about how do we think, how is it reasonable to assume that the errors can be modeled. And different modeling of the errors will lead to different statistical outputs. So given that we have one model, how do we continue? How do we estimate it? Well, the universal method is called maximum likelihood estimation. I will not go through the theory of it, but let me just mention what it does. So again, I assume I have a simulator that produces for me a sequence of data, so capital Y. So Y is not just one value, it's the complete sequence. To simplify here, I assume Y is just a sequence of unidimensional values, but in reality, it can be way more complicated. Doesn't matter. So we assume we have a simulator program that produces data and assume that the joint PDF of all the data that I'm seeing exists. So this PDF has this data comes from a distribution for which, at least in theory, I can write the PDF. And the PDF has a parameter theta, which is the thing I want to estimate. Then the idea of maximum likelihood estimation is to say, I take the value of the PDF for exactly the samples that I have seen, what nature has provided to me. I put this value into this joint PDF, and I say that the most likely theta that I should take is the one that has the highest value. It's based on the primitive or intuitive idea that what I see, because I've seen it, it was more likely than things I have not seen. That's the intuition. But of course, there is a stronger theory behind that. The theory says that if the amount of data that you have is large enough, how this is quantified is by using things like the Fisher information that we might discuss a bit later, that if the amount of data that you have is large enough, then this will converge in the limit where you have more and more data. It will converge to the true value. So that is what it means, consistent. And it's robust in the sense that it does not depend on how you model your data. It doesn't depend on the scale in which you write your data. Whether you take the log or the natural value, this is completely independent of the scale. So this is robust, doesn't depend on a reparameterization of your system. If you have two equivalent formulation of the system, but that, for example, one looking at data in log scale, one looking in natural scale, or one that parameterizes theta in a different way. For example, when we have Gaussian models, we can use as parameter the standard deviation sigma, or the variance sigma square. This is the same, morally speaking, but when you do the math, it's not the same to minimize a square or to minimize the square root of a variance here. So all those details are completely, have no impact. Whatever you do, you will find the same estimate. And it is consistent in the sense, as I said before, that if you have large amount of data, the more data you have, if your model is true, then you will, in the long run, get the true value. So because of those properties, this is often used. Let's see what this means for the first of our models. The first model was this one. Our data point are the exponential plus noise. Here, to recap, Ti are supposed to be known. We assume that the times at which we did the first observations are exactly known. There is no error on that. That's a very common assumption. There might be cases where they are not known, in which case you need to put noise here in the times as well. That will give another model, usually very complicated, but that is also possible. Plus noise. A and alpha are fixed but unknown. That's what we want to get. And we assume that epsilon I is IID from a Gaussian distribution with zero mean and same variance tool. If we do that, then we need to compute what is the joint PDF of all the points we have. Now, the joint PDF, well, you look at the textbook on stochastic processes, or you look at the appendix of our lecture notes, and you will find the PDF of a joint Gaussian vector. So here, y is a Gaussian vector because every coordinate is a constant plus a component epsilon I of an IID sequence. So the PDF is simply the product of the marginals. And if we do the math, we find this formula. Each of the value of yi, we give exponential minus square terms, and we take all the products and gives the sum in the argument of the exponential, and all the normalizing terms will multiply together to give this formula. So this is a standard formula that you can find in many textbooks, including the lecture note of this course, for the PDF of such a model here. So now the problem becomes how to maximize this quantity where the optimization variables are A, alpha, and sigma, and where y is my data point. So I plug into this the values that I have observed, and I maximize this with respect to the parameter. In theory, we can do it by calling any optimization method, but for this type of model, there is a very simple result, which is if we have a model of this type, statisticians call it homoskedastic model. This complicated word means homo means same, and skedastic means, I'm not sure exactly, but it probably means variability or something like that. It simply means it's a model with same variance. The error term is additive and is same for all terms. Very important to screen whether this model makes sense, right? Very important to remember. If we have the homoskedastic model with noise term that is assumed to be Gaussian, then it's very simple to this optimization problem as a solution that is obtained as follows. What we need is to minimize the least square, minimize the square error. This is why this is doing least square. The square error is for every data point y, I compute the difference between the data points and the theoretical value that I should have had. And I look for a value of the parameter that minimizes this. This is for the parameter, which is probably the value of interest. Sometimes we're also interested in estimating the variance in order to do predictions, for example. Then the variance is simply this quantity. What is this quantity? Well, this is the sum of the squares of the residues. So the residues, this is the value of the point that we have, our data, minus what we have estimated, what it should be if there would be no noise given our estimated value of the parameter. So this is a residual error after fitting. We take the average over all data points, and that gives us the estimate of the variance here. To put it differently, that means that when we do this, apply the statistical methods to estimate this model, we do exactly the same as if we apply the signal processing method with a score equal to least square. So take-home message, least square score corresponds to the homoskedastic model or to Gaussian IID noise. There are two ways of saying the same thing. We'll do the proof of this result, not because we like to do proofs always, but I think once in a while it's important to have an idea of what is the magic behind in order to see that it is not magic, but why those way of looking at things are powerful here. This is the PDF that I had for my complete data sequence. I have obtained Y1, Y2, etc. This is the formula we have seen a few slides ago. So I want to maximize this because it's a formula that has lots of exponentials. It's more convenient to take the log. So I take the log, that has a name, it's called the log likelihood. That gives me this quantity, minus I log sigma, that comes from this sigma to the power 2i. Plus there is the 2 pi everything, but this thing, we don't care about it because in the estimation, we want to find sigma and beta here. And this 2 pi is a constant. The number of data points, I, is a constant. So this thing here has the same value for all values of the optimization variable sigma pi. So we can ignore it. I call it minus a constant here. And then the log of this, which gives this value here. So the problem is to maximize, minimize this with respect to sigma and beta here, which is the same as maximizing this thing here. So how do we maximize this? Well, there is this annoying thing about sigma. So the way to break the annoyance is to maximize in 2 steps. which is a trick that can often be done when one of the steps is easy, as will be the case here. So I first maximize for a given beta, and say, for any beta, what is the max of that? What is the sigma that reaches the max of that? Why is it easy? Well, because it's a function of one variable that has a closed form. I can compute the derivative. I set the derivative to 0, 1 over sigma plus, etc. And I obtain that for a given beta, the value of sigma that maximizes this is given by this formula, which is very interesting for us because it has a physical interpretation. For a given beta, the value of sigma that maximizes this term, that maximizes the likelihood, minimizes this term, is the average error, square error. Y minus f, that's the error. So we take the L2 norm of the error divided by the number of data points. This is the average square error. That's an interpretation that's very easy. This is why those methods are used a lot, because they have easy interpretation. We interpret the variance of our model as the average square error that we've seen after fitting. So this is assuming beta is given, but beta is of course not given. So if we want to maximize over two blocks, sigma and beta, then we can first take the maximum for a given beta that gives us the sigma hat, and then the max is associative. Max over max is the overall max. So what we need now is find the beta that maximizes this. I said max, the same holds for min. We max in the likelihood, but because of the minus sign, we minimize this thing here. So we want to find the beta that minimizes this quantity. And here you recognize the main statement of our theorem. The value of beta that is the result of maximum likelihood optimization is the one that minimizes the L2 norm. So it's the beta that is provided by least square. So that shows that if we apply maximum likelihood estimation to this model, then in fact we can do least square. Interestingly, least square gives us not just beta, but sigma also, because we know the value of sigma for a given beta. It is given by this. And if beta happens to be exactly minimizing this, with a bit more of math, we can see that the log likelihood is exactly minus I log of sigma hat of beta plus a constant here. So that tells us two things. That gives us first the value of sigma. Once we've minimized, we found the beta that minimized, that gives us an estimate of sigma. And that gives us also the likelihood. Why we need the likelihood? Well, we will see that when we want to do more sophisticated model fitting, for example, in view of prediction, then we will need also the likelihood. So right now, remember that for such models, we obtain very easily not just the parameters, but also the optimal likelihood. Back to our example. The first model, where we assume the growth is such that the error terms are of the same variance at every data point here, then we find sigma that minimizes this. We find alpha hat and a hat that minimizes the square error, and sigma given by this formula. Now, a benefit of the statistical method is that because we have modeled the error, we can verify whether our model makes sense. So we can do a posteriori verification of whether our model makes sense by simply computing the residuals. So here with this model, we have the residuals, which are the error, the difference between the theoretical value for the fitted value of A and alpha minus the true data. So I plotted them here. You see they are zero mean. They are around zero. I plotted them for the model in natural scale and for the model in log scale here, for the model 3. And now we can discuss. Once we have plotted the model, we can discuss, was our assumption correct or not? First, I should give a warning. In reality, verifying that an assumption is true or not becomes a second order problem that is usually very difficult. So you need zillions of data points to verify exactly assumptions. And most of the time, when you have zillions of data points, you find that the assumptions are did not fit exactly, were not correct. But This will give us a method for discriminating between families, classes of models. For example, here between model 1 and model 3, in model 1, we say the noise terms are all independent and have the same variance. And we say the same thing for model 3, but the noise terms are computed different. Obviously, for model 1, this is not correct. We see that most noise terms for the small values are very small, and for the large values, they become larger here. So obviously, the variance here increases as we go along the x-axis. Here, well, we don't see any violent discrepancy with this assumption here. So this is what I could say here. A posteriori, I could say if I have to compare model 1, which fits in the natural scale, with model 2, 3, that fits in the log scale, then I would prefer model 3, because by looking at the residuals, I see that the error terms seem to be more natural, fitting better the almost stochastic model that I do in this scale. Of course, we could have seen this by looking at the data from the beginning, but the important thing is to know what we should look at. So the error term here is not consistent with my model. Therefore, probably the prediction is better for model 3 than for model 1. So first summary of what we've seen is that if we have a model where theoretical model plus additive noise, then there's equivalence in saying that the score is the least square, and the noise has the same variance all across my data series. This is very often done, but if you think about it, there's very little chance that this is true, right? If you measure the state of an infection where at the beginning nobody's infected, the error you make when counting things is probably not of the same amplitude as when you have to count millions of devices here. So it is rarely the case that the errors produced by a counting system or an experiment or observations are of the same magnitude all along the axis of the model, of the experiment here. So very often it's better to try to put weights like model 2 was doing. Model 2 says that the noise term is proportional to the value, to a theoretical value. So this is the same as saying that there is some noise here, Wi, that the variance of the noise is not the same, but depends on some weight here. So if you put the weight on the denominator at the variance, it is the same as putting here at the numerator for the score function. So this is called weighted least square. The larger the weight that you give, that means the less the variance is. So you give more weight to data points on which the uncertainty is smaller, which makes sense from a statistical viewpoint. If the uncertainty is believed to be smaller, then you give more weight to them in the fitting problem. So we have seen 3 models. We have seen a theory of how to compute scores for fitting the model. Which score corresponds to which of these models? I close the poll in a second, in a few seconds. Closing now. And a lot of abstentions, and those who voted unanimously for the A, the first answer, which is the correct one. Let's see why. Well, the first one is the exactly one-to-one mapping of least square, so that's easy, right? That's the least square error term. Now the model 2. The model 2 can be written as in this form here. The WI is 1 over this term here, so it is the same as saying that this is the score, right? So the good news is model 2 can be fitted as well as model 1. There's no reason to use model 1 just for tractability. Model 2 makes a lot of sense. If we look at the data, we see that the error probably increases with the value. And if we don't know how it increases, making it proportional is more reasonable than making it constant. That gives this term here. Model 3, well, model 3 is the same as model 1 from the viewpoint of the method to compute the score. So that gives me exactly a least square score, but in log scale, in the log of the data and the log of everything here. That gives me this. So this is how we can compute the score. So first take-home message, there is no reason for jumping into least square before you should think about your model. And here, obviously, 2 or 3 are things that make more sense. So you should use 2 or 3 for fitting your data. By the way, are they the same, 2 and 3? Or, well, as we discussed before, they are not exactly the same, because if I take model 2 and I take the log of model 2, I will obtain log y is equal to this, those are all constant, plus log of 1 plus epsilon. So model 2 is not the same as log model 3, because if epsilon is Gaussian, log of 1 plus epsilon, this is a nonlinear transformation. It is not Gaussian. It's a complicated distribution. However, if the noise is not too large, which most of the time we expect is the case, otherwise the fitting is going to be very difficult. If the noise is small, so remember here, this is the relative noise, it is the relative error. So if the error is a few percent, then log 1 plus epsilon for such epsilon is almost equal to epsilon here. So when the error in relative terms is small, this is equivalent to that, which is model 3 here. So take home message, if the error terms are reasonable, model 2 and 3 are equivalent. So fitting this or fitting that should produce very similar results, which is very reassuring because we have no real reason to prefer one or the other model. So take home message, in order to fit a model, you need to find an appropriate score function. One easy way to determine a score function is to consider an explicit model of the noise and verifying it by looking at residuals. And a common mistake is to assume that noise has same variance across all the experiments. Sometimes it's hard to verify, but even if we look at our first example here, right, if we look at this data here, we see that obviously the errors that we were doing in the first data points were very small because everything is very small here. And we see that here the errors are very large. So there is large variability compared to any exponential here. So after fitting this, we should wonder whether the least square fit was really appropriate, even if we don't know about all the theorems and the methods that we are seeing now. So take-home message is same variance, be suspicious about it. The fitting might be completely wrong. Now what we will see next, we'll see next week in fact, is that once we have a model fitting, a model that fits well and we think the residuals are roughly speaking consistent with what we see, then we can do more than just fitting the model. We can also fit the noise, and with the noise we can do, for example, predictions here. How we do this is very simple if the model is linear, and this is what we will discuss in detail next week. We will also see that the Gaussian error term, which is very, very commonly used, is perhaps not the best one. So next week, we will discuss how having other distributions of the noise which are the ones that are used, for example, by geophysicists, but very little known in computer science, how those other distributions make a lot more sense and how to use them in practice. This we will discuss also with linear models. Voilà, with 5 minutes of earliness, I will stop here today. So that's all for this sequence, because the other sequence would break in the middle of a complicated chapter. So I prefer to do it next week. And also because you have a lab to complete. So I'm sure you're happy to have more time for the lab. That's all for today. I wish you a good continuation of the lab. And don't forget to complete the quiz on queuing that is ongoing for some of you. And I wish you successful continuation.